Hello, my name is Arya Gupta, and I'm presenting the paper Inducing Lattices in Non-Lattice-Linear Problems. In this presentation, we will discuss synchronization. Specifically, we will discuss eliminating synchronization, some ways how to do that, and what the theory behind those ways looks like. Let us start with a discussion on the structure of a distributed system. There are several nodes, and every node I contains guards and corresponding actions. The structure of a guard looks like this. G implies A sub C, where G is the guard and G is a Boolean expression of variables of multiple processes, and A sub C is the action, and A sub C is executed at process I when I evaluates G to be true, and A sub C makes changes to the variables of the node I, process I. There is an underlying assumption in most distributed system algorithms that we see, and that assumption is G is evaluated in the current state. It means that the values of variables of the processes that G is evaluated on are assumed to be the fresh values, to be the latest values. To ensure this assumption, we need synchronization. Synchronization is needed to ensure that the data is read consistently. And depending on the problem and depending on what the algorithm wants, what the algorithm needs, we can use different types of synchronization. So extending our discussion towards asynchrony, what we want to do, we want to design the guards in such a way that they enable the nodes to take decisions such that a value once discarded is discarded forever. In this figure, there is a system that we are trying to depict. There are several nodes. Let's see the behavior of node 2. So in node 2, it transitions from 1 to 2 to 3 to 4. So let's study the transition from 3 to 4. It only transitions from 3 to 4 when the guards decide that 3 is not a good local state for any optimal global state. Similarly, if it decides that 4 is also not a good state for any optimal global state, then it moves to 5. It does not go back to 3 or 2 or 1 because it has already discarded 1, 2, and 3 such that it has decided that all these 3 values, they are not good for any optimal global state. So it does not have to go back. It only has to move forward. So it goes from 4 to 5. So if the predicate can determine that a local state is not viable for any global state, then we can allow the nodes to run in asynchrony. Here we see that the local states of individual nodes, the local state that they visit, are forming total order. A total order is being induced because they are able to take such strong decisions. So they don't have to go back, and that's as a result they have a total order. Now, if there is a total order, the global states form a lattice. Meaning if there is a total order among the local states visited by a node for all nodes, then the global states form a lattice. Now, a node that is in a bad state is called impedanceable node. And this word impedanceable is a conjunction of two English words, impediment and indispensable. And it is called impedanceable because that bad node is the node that is in a bad local state is an impediment to progress if it does not execute, and it is indispensable to execute for progress. Let's study an example problem, the minimal dominating set problem. In this problem, a node, a node is dominated if it is in the dominating set, and it is also said to be dominated if one of its neighbors are in the dominating set. And the task here is to compute a dominating set for the graph G, meaning all the nodes should be dominated, but the nodes should be chosen in such a way that the set is minimal. Let's consider this graph, this example graph, a graph of two nodes connected to each other by an edge. And let's consider this example algorithm on this graph. So node 1 uses this algorithm. If node 1 sees that node 1 is out and node 2 is also out, then node 1 changes its state to in. Otherwise, if it sees that node 1 is in and node 2 is also in, then it changes its state to out. So it changes its state to in only when it decides that there is not a dominating set in the graph, and it changes its state to out when it decides that we are in a dominating set, but we can still remove, but it is not a minimal dominating set. So let's see the working of the implementation of that algorithm when the nodes execute not in an interleaving fashion, and also there are no implementation of any locks. So in state 4, for example, we see both the nodes are out. Now node 1 reads that both the nodes are out, and node 1 decides to move in. And at the same time, node 2 also reads for assumption that both the nodes are out, and node 2 also decides to move in. So state 4 transitions to state 3. Now in state 3, both the nodes are in. If again both the nodes read the states of each other at the same time, they both will decide to move out. So state 3 will transition to state 4, and this can continue forever. So here we see that if only one node is allowed to execute at a time step, then we can guarantee convergence. But if both the nodes are allowed to execute simultaneously, then the global state may never converge. Extending our discussion towards asynchrony, Garg in 2020 introduced lattice linear problems. And the problem that we are going to study is the stable marriage problem. In this problem, we have men and women. Men propose to women, and women accept or reject that proposal. Men have preference lists, and women rank men. So in this example, we are going to study where there is a system where there are 3 men and 3 women. So all the men start with their first choices. So all of them are proposing to their first choices. A is proposing to Z, J is proposing to Z, and T is proposing to K. So A and J are, they have a conflict because they are proposing to the same woman. Now let's see what Z has to say about it. Z prefers A more than J. So in here, we have that J is impedanceable. So J moves to the next choice. So J is now proposing to K, but T is also proposing to K, and A is proposing to Z. So J and T have a conflict now. But let's see what K has to say about it. K prefers J more than T. So this time T is impedanceable. So T moves from local state 1 to local state 2 and start proposing to the next choice. So this time T is proposing to M, J is proposing to K, and A is proposing to Z. So we have no conflict, and we have reached the optimal global state 1, 2, 2. In this example, we make some observations here about the properties of this of such a system, that all the nodes, they are the states that they visit, they are forming a total order, because a man only moves forward from choice 1 to choice 2 to choice 3, and there is no point coming back. So the states that every node visits form a total order, that the individual nodes visit form a total order. And as a result, we see a lattice being induced among the global states. Another property that we see is that this system has to start from the state 111. The initial state has to be 111. Otherwise, we might not be able to reach the optimal global state, which is 122. So this idea, it cannot be directly extended to some of the problems, and one of those problems is the minimal dominating set problem. So here we were able to, given any suboptimal global state, we were able to decide which of the nodes is impedanceable, which has to move. And that does not follow here, which makes it a non-lattice linear problem. And let's see with an example how that works. In this example, again, this is a graph of two nodes. Both the nodes are out. So either two can move in or one can move in, leading to both such transition will lead to separate optimal states. So when two moves in, we have that in this transition, two is impedanceable here. And according to this transition, one is impedanceable here. So we have a problem here. We cannot actually determine which node is impedanceable, and that's why the minimal dominating set is a non-lattice linear problem. To address such issues, we presented eventually lattice linear algorithms, and we introduced such algorithms in 2021. And in that paper, we also presented an algorithm for the minimal dominating set problem. In such problems, only a subset of the states form a lattice. So a lattice is not induced in the entire state space, but only a subset of the state space. And that's why we call it eventually lattice linear algorithms. This paper considers three questions. What other problems can be solved under lattice linearity? Can we induce lattices in the entire state space in non-lattice linear problems? And are there problems that allow self-stabilization? So we have an algorithm for dominating set, minimal dominating set, and we use the following macros. If I is removable, I is removable if and only if I is in the dominating set, and all the neighbors of I will stay dominated, including I. Those nodes will stay dominated even if I changes its state to out. I is edible if and only if I is not being dominated. I is unsatisfied if and only if I is removable or edible. To determine if I is impedanceable, I has to be unsatisfied. And second condition is for every node j within distance 2 of I, this is important, distance 2 of I, j should not be unsatisfied. Or if j is unsatisfied, then the ID of j should be less than the ID of I. The algorithm is as follows. If I is impedanceable, then I will toggle its state. If it is in, it moves out, and if it is out, it moves in. Now, why did we choose the distance 2 tiebreaker? If we don't implement a tiebreaker at all, if we don't compare IDs, then two adjacent nodes may try to leave the dominating set, which might make the dominating set non-minimal. Not non-minimal, non-feasible. We may not have a dominating set anymore. Or two adjacent nodes may try to move into the dominating set, which this action might make uh, a dominating set feasible but not minimal. So this is problematic. Now, if we choose only distance 1 in our tiebreaker, then two nodes at distance 2 from each other may try to leave the dominating set, and some other node between them might become not dominated. So we see an example here, a path of 5 nodes, where node 1, node 2, 4, and 5 are in the dominating set, node 3 is out, and node 2 and 3 decide that they are removable, so they can move out, which makes node 3 was dominated earlier. Now it is no longer dominated, so we have a problem with distance 1 as well. And that's why we used distance 2. So under distance 2, a node, when an unsatisfied node, edible or removable, when an unsatisfied node makes a transition, changes its state, it no longer stays unsatisfied. So as a result, we see lattices being induced in the state space. So we see an example graph of 4 nodes where there are 2 edges being induced, 2 disconnected edges. Let's see this example state where all the nodes are in. So if all the nodes are in, V2 will move out and V4 will move out. In this state, this state, V4 moves out, and in this state, V2 moves out. And eventually, when both the nodes move out, we obtain this state. So this is a lattice that is being induced among these 4 global states. And this is an optimal state. We have also an algorithm for coloring. In coloring, we use the following macros. A node I is conflicted if some neighbor of I has a color same as that of I. A node I is reducible if it can reduce its color value without a conflict. An unsatisfied node is conflicted or reducible. Now, while deciding impedanceable, I has to see all other nodes and compare IDs in this particular problem, in this particular case. And an impedanceable node changes its color value and obtains the minimum possible color value that does not face a conflict. We also have an algorithm for vertex cover, but in this case, we require a distance 3 tiebreaker to ensure that there is no race condition among the nodes as they execute. In conclusion, we have that lattice linearity implies that said algorithm can be run without synchronization. We presented lattice linear algorithms for non-lattice linear problems, dominating set, coloring, to approximation vertex cover. In these cases, vertex cover is not stabilizing, whereas coloring and the algorithms for coloring and a minimal dominating set are self-stabilizing. So lattice linearity and their parallelized versions can be extremely useful in computational applications because they allow the nodes to run in asynchrony. We have some open questions. What other problems can we apply lattice linearity in? What existing algorithms exhibit lattice linearity? Whether a self-stabilizing algorithm can be developed for 2 approximation vertex cover? And what other approximation algorithms can be developed under lattice linearity? Thank you.